Right now, over the South Atlantic, Earth's magnetic field is falling on a curve that some scientists read as the opening act of a full magnetic reversal. Right now, over the same patch of ocean, other scientists read the same measurements and see nothing more than a recurring wobble that has happened before and will pass. Both statements have been defended in print, in peer-reviewed journals, using the same satellite data drawn from the same missions in the same years. That is the strange position we are in. The measurements are not in dispute. Nobody argues about the numbers coming down from orbit. What splits the field, quite literally the field of geomagnetism, is what those numbers mean about the next century, the next millennium, and the deep behavior of the churning iron beneath our feet. To sit with this question honestly, you have to hold two readings of the same evidence in your head at the same time, and you have to resist the pull to pick a side before the science does. Start with what everyone agrees on. Earth carries a magnetic field generated deep inside its outer core, where liquid iron and nickel churn in vast slow currents nearly 2,000 miles below the surface. Scientists call the process the geodynamo. The motion of that metal, driven by heat rising from the inner core and by the planet's rotation, generates electric currents, and those currents generate the magnetic field that surrounds the whole planet and reaches far out into space. That field is not uniform. It is stronger at the poles, weaker at the equator, and in one particular region stretching from Brazil across the South Atlantic towards southern Africa, it is weaker than anywhere else on Earth. That weak region has a name. Scientists call it the South Atlantic Anomaly, and satellites have been mapping its shape and depth for decades. Inside the anomaly, the field intensity dips low enough that radiation from space presses closer to the surface than it does anywhere else on the planet. Spacecraft passing overhead absorb higher doses of charged particles. Onboard computers glitch. Some missions shut down non-essential systems as they cross the zone and switch them back on once they are clear. The anomaly is not new. Records of the field going back to the 1800s, drawn from ship-based magnetic surveys and observatory measurements on land, show a weak patch in this same general region even then. What is new, or rather what has become measurable in the last 3 decades, is how quickly the anomaly is changing. Global satellite coverage began in earnest with the Danish Ørsted mission launched in 1999, followed by the German CHAMP mission in 2000, and then by the European Space Agency's Swarm constellation, 3 satellites flying in formation since 2013. Together, these missions have given scientists something they never had before: a continuous, high-resolution, planet-wide picture of the magnetic field updated week by week. And what that picture shows is straightforward. The field over the South Atlantic is weakening faster than the field almost anywhere else. The dipole component of Earth's total field, meaning the simple bar magnet part of it, has dropped by roughly 9% since about 1840. Over the anomaly itself, the local drop has been steeper. Then, in 2020, analysts working with swarm data noticed something that changed the conversation. The anomaly was no longer behaving as a single connected weak zone. A second minimum had opened up on the eastern side, drifting towards southern Africa, while the original minimum continued its slow westward march across South America. What had been one dent in the field was becoming 2. On one side of the question stand the modelers, many of them working at NASA's Goddard Space Flight Center in Maryland, in close collaboration with the international teams that build the reference models geophysicists rely on. They look at the accelerating drop, at the split into 2 lobes, at the reverse flux patches visible in the flow at the core mantle boundary, and they see a pattern that shows up in computer simulations of the early stages of a magnetic reversal. They are careful. They do not say a reversal is happening. They say the behavior is consistent with what a reversal's opening centuries would look like, and that this possibility can no longer be dismissed. On the other side stand the paleomagnetists, and the group most often associated with this reading works out of the University of Rochester in New York, led by John Tarduno. They study the field's behavior not over the 25 years of the satellite record, but over centuries and millennia, using traces of magnetism locked into ancient burned clay, volcanic rock, and archaeological hearths. When they look at the same anomaly, they see something the satellite era simply cannot see on its own. They see precedent. They see a region that has flared like this before, at least twice in the last 1,500 years, and recovered each time. Their reading is that the current weakening is not the beginning of a reversal, but the latest turn in a recurring cycle driven by something buried far below the anomaly itself. Give the modelers the floor first, because their case rests on something the paleomagnetists cannot match. They can watch the field move almost in real time. At Goddard Space Flight Center in Greenbelt, Maryland, a small group of geophysicists spends its days translating raw satellite readings into moving pictures of the deep Earth. The lead figure most often cited in this work is Weijia Kwang, whose core flow modeling has, for more than 2 decades, served as one of the reference points for how the field is expected to behave. Alongside him, Terry Sabaka has built and rebuilt the mathematical descriptions of the total field that other agencies borrow from. Their group contributes to 2 of the models geophysicists everywhere depend on. The first is CHAOS, developed jointly with the Technical University of Denmark and updated almost continuously from swarm data. The second is the International Geomagnetic Reference Field, revised every 5 years by an international working group in which Goddard is one voice among several. Their argument, in its own terms, begins with a simple observation. The field is not just falling, it is falling faster than the long baseline suggests it should. Over the whole satellite era, the global rate of decrease has held near 5% per century. Over the South Atlantic anomaly itself, the local rate has been closer to 2% per decade in some measurements. That is a large gap between the global average and the regional signal, and it is the gap that first drew the modelers' attention. When they take the numbers and run them forward, holding the current rate steady, the local minimum inside the anomaly reaches values comparable to what the field looks like during a reversal in numerical simulations, on timescales of hundreds to a few thousand years. Nobody at Goddard says that projection is a prediction. They say it is what the current trajectory implies if it does not change, and that the honest scientific question is whether it will. The second piece of their case is what they see when they look downward through the data, not just at the field at the surface, but at the pattern of flux at the core mantle boundary itself. This is a delicate step because nobody has ever been to the core mantle boundary. The deepest borehole ever drilled reached about 7.5 miles, and the boundary sits near 1,800 miles below the surface. Everything scientists know about the flow of iron at that depth is inferred from magnetic measurements taken far above, filtered through equations that turn a surface field into an implied pattern of motion in the liquid metal below. It is more like reading a sonar image than looking through a window. But the technique has been refined for nearly 40 years, and its outputs have become detailed enough that specific features can now be tracked from one satellite mission to the next. What the Goddard modelers see beneath the South Atlantic is not a smooth outflow of magnetic flux. They see patches where the flux goes the wrong way. In most of the world, field lines emerge from the core in a pattern consistent with the ordinary polarity, north emerging where north should emerge. But in a growing set of regions clustered beneath the anomaly, the field lines reverse direction locally, curving back down into the core instead of flowing outward. These are called reverse flux patches, and they are not a new discovery. What is new, and what the modelers keep coming back to, is that they are spreading. Satellite data across the swarm era shows the reverse flux area beneath the South Atlantic growing measurably, and at least one large patch drifting slowly westward beneath the African plate. Here is why that matters to the reversal reading. In numerical simulations of the geodynamo, the opening centuries of a magnetic reversal do not begin with the field flipping cleanly from one polarity to the other. They begin with reverse flux patches appearing at the core mantle boundary, growing, spreading, and eventually overwhelming the dominant polarity in specific regions before the reversal propagates outward. The pattern the modelers see in swarm data is not identical to any single simulation, but it sits inside the envelope of what those simulations produce during the early stages of a reversal, and that envelope is not something earlier generations of geophysicists could compare against real data. The simulations only became detailed enough to be useful in the last 20 years, and the satellite record has only just become long enough to test them. 2 additional lines of evidence sit behind the argument. The first is the split itself. When the anomaly began separating into two lobes, one drifting toward South America and one toward Southern Africa, the modelers went back to their simulations and looked for analogous features. They found them. In several simulated reversals, the field does not weaken as a single connected zone. It weakens in multiple centers that grow, drift, sometimes merge, sometimes divide, before the global polarity begins to break down. The observed split is not, by itself, evidence of a reversal. But it is the kind of thing the reversal simulations produce, and it is not the kind of thing a stable field usually does over the course of a single human generation. The second is the acceleration. The rate of change of the field, what geophysicists call secular variation, has been running higher over the last decade than the pre-swarm baseline predicted. When the International Geomagnetic Reference Field was revised for the 2020 release, the working group had to include a mid-cycle update because the field had drifted faster than the previous model anticipated. That update is one of the reasons the argument gained visibility outside the technical literature. If the field's own rate of change is itself changing, then the assumption that the current weakening will simply continue at today's pace is probably too conservative. The modelers do not know which direction the acceleration will go. They point out only that a stable, boring field does not usually force off-cycle model revisions. They are careful about what all of this adds up to. Nobody at Goddard or at any of the collaborating agencies says a reversal is happening now. The last full reversal, the Brunhase-Matuyama transition, took place roughly 780,000 years ago, and reversals of that scale unfold over thousands of years, sometimes longer. What the modelers say is narrower and, in some ways, more unsettling. They say the pattern currently visible in the data, the accelerating drop, the split, the spreading reverse flux patches beneath the anomaly, is the pattern a reversal's opening act would produce if one were beginning. They cannot prove it is beginning. They cannot rule it out. And in a field where cannot rule out has usually meant extremely unlikely, the fact that they are no longer willing to close that door is itself the point. To reach the other side of the argument, you have to leave the satellites behind and go looking for the field's fingerprints in things people burned 1,000 years ago. The person most closely identified with this reading is John Tarduno, a paleomagnetist at the University of Rochester in New York, who has spent the better part of 3 decades pulling the ancient magnetic field out of rocks and archaeological remains on almost every continent. His group's work on the South Atlantic anomaly did not start as a project about the anomaly at all. It began as a broader effort to reconstruct the behavior of the field across southern Africa, going back into the Iron Age, using a source of evidence that most geophysicists had overlooked for decades: burned clay floors from Bantu-speaking farming villages. The technique behind this work is worth understanding in its own right, because the entire wobble reading depends on trusting it. When clay is heated above a certain temperature, roughly 1,000 degrees Fahrenheit, the magnetic minerals inside it lose their existing orientation and, as the clay cools, lock into alignment with whatever magnetic field is present at the time. The clay becomes, in effect, a frozen snapshot of the field at the moment of cooling. Volcanic rocks do the same thing, which is how paleomagnetism first became a discipline in the mid-20th century. But volcanic rocks erupt where they erupt, on their own schedule, and they are unevenly distributed across the parts of Earth where the anomaly's history matters most. Burned archaeological features, by contrast, come with a human record attached. Their locations are documented. Their approximate ages are known from pottery styles and radiocarbon dating, and in southern Africa, they cluster in exactly the region sitting under the modern anomaly. Tarduno's group focused on a particular set of sites in what is now the border region of South Africa, Botswana, and Zimbabwe, where Bantu-speaking communities practiced a ritual response to drought that turned out to be scientifically valuable centuries later. During severe droughts, villagers would deliberately burn their grain storage huts and cattle enclosures as an offering, then rebuild them. The floors of these burned structures cooled through the magnetic locking temperature and preserved a directional and intensity record of the field over the region at that exact time. The Rochester team, working with archaeological collaborators, sampled dozens of these floors dating from roughly 400 to 1,600 years ago. Their 2018 paper in Geophysical Research Letters, followed by further work, produced a claim that changed the shape of the debate. The field over southern Africa, they showed, had done something like the modern anomaly before, at least twice, once between roughly 400 and 600 AD, and again around 1300. In both intervals, the local intensity dropped substantially and the field direction wandered, and in both cases, the drop was followed by recovery. The modern anomaly on this reading is not a novel event at all. It is the third turn of a cycle that has been running for at least 1,500 years and probably longer. This is the paleomagnetists' opening move, and everything else in their case builds on it. If the anomaly has happened before, the modeler's projection loses its unique weight. A trajectory that looks alarming across 25 years of satellite data looks quite different across 1,500 years of clay floors because the same trajectory has, on the paleomagnetic evidence, appeared and vanished twice already without producing anything resembling a reversal. But Tarduno's group does not stop at the observation. They also propose a mechanism. The reason the anomaly keeps flaring in this same region, they argue, is that something specific sits beneath it. The African large low-shear velocity province, the continent-sized structure at the core mantle boundary that seismic waves slow down as they pass through, is not just an odd feature of the deep Earth. It is a persistent source of instability in the flow of iron in the outer core directly above it. Whatever that structure is made of, and there are competing ideas about its composition, its presence disturbs the currents that generate the field. The same disturbance, over and over, in the same place, produces the same kind of weakening, over and over, in the same place. On this reading, the anomaly is not a symptom of something changing. It is a symptom of something that has been there for a very long time and periodically expresses itself at the surface. This framing gives the wobble reading its most important asset. It offers a reason for the recurrence, not just an observation of it. Without a mechanism, the paleomagnetic evidence could be dismissed as coincidence. With one, it becomes a scientific proposal that predicts specific things about where the weakening should recur, which is beneath the Lille FWP, and how it should behave, which is as a bounded instability that flares and settles rather than a runaway process. The Rochester Group has extended this argument in several directions since the original 2018 paper. They have looked at older paleomagnetic records from the same broad region, drawing on volcanic samples and other archaeological materials, and reported evidence consistent with the same cyclical pattern going further back. Other groups working independently, including researchers at the University of Liverpool and at the Institut de Physique du Globe de Paris, have contributed additional paleomagnetic data from other parts of the Southern Hemisphere that broadly support the picture of a recurring, geographically anchored instability rather than a globally accelerating collapse. Their own honest caveats sit next to the argument. Paleomagnetic sampling is spatially sparse. The clay floor record is concentrated in southern Africa, and while that happens to be exactly where the modern anomaly's African lobe is drifting, it does not give a complete picture of what the field was doing across the whole southern hemisphere during those earlier intervals. The recurrence interval is estimated from a handful of dated events, not measured from a continuous record. Radiocarbon dates carry uncertainties of decades or longer, and the intensity values recovered from burned clay, while carefully calibrated, are not as precise as the numbers SWARM produces from orbit today. Every 5 years, a working group inside the International Association of Geomagnetism and Aeronomy, an arm of the broader International Union of Geodesy and Geophysics, sits down to produce a single mathematical description of Earth's magnetic field that the rest of the world will use until the next revision. Airlines rely on it to align runway headings. Smartphone compasses depend on it. Directional drilling in the oil and gas industry, submarine navigation, satellite orientation, the calibration of scientific instruments in dozens of unrelated fields, all of it flows downstream from the numbers this working group agrees on. The product is called the International Geomagnetic Reference Field, and its revisions are numbered in sequence. The most recent full revision, released at the start of 2020, is the 13th. The current cycle, aimed at a 2025 release, is the 14th. The working group does not build the model itself. It receives candidate models from a set of participating institutions, each of which has submitted its own best description of the field, based on its own analysis of the available satellite and observatory data. Goddard submits one. The Technical University of Denmark submits one. The British Geological Survey submits one. Germany's GFZ Potsdam submits one. So do groups in France, Russia, China, and Japan. The working group then compares the candidates, weighs them, and produces a consensus model that draws on all of them. That process has, for most of its history, been technical and quiet. In the last 2 cycles, it has not. The trouble began in the run-up to the 13th revision. As candidate models came in from the participating institutions, the working group noticed that the field over the South Atlantic was drifting faster than the 12th revision had assumed it would. The 12th revision, released in 2015, had included a term for secular variation, meaning the rate at which the field is changing, that was calibrated against data available up to that point. By late 2018, it was clear that the observed rate had outrun the model's assumed rate to a degree that mattered for the applications downstream. Airlines were seeing their magnetic north references drift by more than the model predicted. The working group took an unusual step. It issued an out-of-cycle update to the 12th revision in 2019, a full year before the scheduled release of the 13th. The update was not a scientific dispute. It was a practical necessity. But it was also, quietly, an admission that the field's behavior over the South Atlantic had exceeded what a 5-year model window could safely absorb. That off-cycle update is the event where the 2 readings first collided in a way the wider scientific community could not ignore. The modelers pointed to the update as vindication. If the field were behaving inside the range of a stable, cyclical wobble, they argued, a 5-year model should have held for its full 5 years, as previous revisions had. The fact that the 12th revision had to be patched mid-cycle meant that whatever was happening over the anomaly was moving faster than the working group's assumptions could contain. To the modelers, this was the same acceleration they had been describing in the technical literature, now expressing itself as an operational problem for the people who use the model to fly airplanes and drill wells. The paleomagnetists read it differently. To them, the off-cycle update revealed less about the field than about the model. 5-year revision cycles, they pointed out, were designed in an era when the assumption of slow, steady secular variation was reasonable because the historical record used to build the models was itself slow and steady. If the underlying field is capable of moving faster in some intervals than in others, as the paleomagnetic record suggests it has done many times, then the 5-year cycle was always going to break down eventually. What the 2019 update showed, on this reading, was not that the field is doing something unprecedented. It was that the modeling framework had underestimated the range of behavior a normal, recurring instability can produce. Neither side conceded. Both cited the same event as evidence for their position, and that was only the beginning. The formal 13th revision, released in December 2019 and effective from January 2020, incorporated data through the middle of 2019 and adjusted its secular variation terms upward to reflect the observed drift. When the modelers ran that revision forward and compared it against the paleomagnetic reconstructions the Rochester Group and its collaborators had published, the 2 projections disagreed sharply about what the next century would look like. The 13th revision, extrapolated cautiously, put the anomaly on a course toward continued weakening. The paleomagnetic reconstructions, taken as a guide to the probable range of natural variation, put the anomaly within the envelope of past events that had recovered. Both projections used the 13th revision as their starting point. They diverged on what the trend meant, not on what the current numbers were. The 14th revision cycle has, if anything, sharpened the disagreement. Candidate models submitted through 2024 and into the current review period show the 2 lobes of the anomaly continuing to behave differently, with the African side weakening measurably faster than the South American side, consistent with the pattern the modelers had described in earlier work. Reverse flux patches beneath the anomaly have continued to grow. The dipole moment has continued its long decline. At the same time, new paleomagnetic studies published in the last few years, including work from groups outside the original Rochester Circle, have added further data points to the recurring flare picture, extending the reconstructed history in both directions in time. The working group itself does not take sides in the interpretation. Its job is to produce a mathematical description of the field, not to say what the description means. But the people who sit on the working group are the same people whose institutions publish the interpretive papers, and behind the polite technical discussions of coefficients and error bars, the two readings have been present in the room the whole time. The consensus model that emerges each cycle is a fact both sides can build on. What each side builds is different. Something else has happened during these two cycles, and it is worth naming because it complicates the neat picture of two opposed camps. Both sides have quietly converged on parts of what the other side is saying. The modelers now accept, in a way they did not fully accept a decade ago, that the African LFP is likely playing a role in anchoring the anomaly's location and shape. That was, for years, a paleomagnetic argument. It is now a shared one. Goddard's own recent modeling work explicitly incorporates the influence of core mantle boundary structure on the flow patterns that generate the field, and the LSVP is the largest and most stable such structure in the southern hemisphere. The paleomagnetists, for their part, have moved away from framing the modern anomaly as simply another cycle of the same magnitude as the earlier ones. Recent work from the Rochester Group and its collaborators acknowledges that the current weakening, measured against the reconstructed history, appears to be occurring somewhat faster and reaching somewhat lower values than the events around 600 AD or 1300, even if it remains within the broad envelope of natural variation. That is not a concession that a reversal is beginning. It is a concession that the current event is at the more severe end of what the cycle can produce. So set the two arguments beside each other and ask, honestly, what each has earned. The reversal reading has earned the acceleration. That is not a small thing. For most of the 20th century, the standard picture of the field was one of slow, orderly secular variation with occasional regional excursions, and the assumption that any weakening visible in the historical record would resolve within a human lifetime or two. That picture no longer fits the satellite data. The rate at which the field is changing over the South Atlantic has forced an off-cycle model revision, forced upward adjustments in every subsequent reference model, and forced working geophysicists to treat the anomaly as a live problem rather than a quirk. The modelers were right about that, and they were right earlier than the wider community was willing to accept. When Goddard and its collaborators began describing the pattern beneath the anomaly as consistent with the opening stages of a reversal, the framing was widely called alarmist. It is no longer called that. It is called cautious. That shift in the tone of the technical literature is itself a kind of concession the reversal reading has earned from the field. The reversal reading has also earned the split. The separation of the anomaly into two lobes with different behaviors was not something the wobble reading predicted in advance. It was something the numerical simulations of the modelers had produced, in general form, as a feature of pre-reversal dynamics, and when it appeared in the 2020 data, it fit their picture more naturally than it fit anyone else's. The paleomagnetists have since incorporated the split into their framework as a feature of the current cycle's particular expression. That incorporation is legitimate, but it came after the fact. The wobble reading has earned something larger. It has earned the historical envelope. Before the Rochester Group's work on the burned clay floors of southern Africa, the standard framing of the anomaly assumed, implicitly, that the current weakening was the only such event in the field's recent behavior, because it was the only one anyone had measured. The paleomagnetic evidence changed that framing. It established that similar weakenings have occurred at least twice in the last 1,500 years, in the same region, driven by what appears to be a persistent feature of the deep Earth. That evidence did not exist in the technical literature before roughly 2018, and once it did, no serious interpretation of the modern anomaly could ignore it. Every projection of the field's future course now has to account for the possibility that the current event will resolve the way the earlier ones did. The wobble reading built the floor beneath the whole debate. The wobble reading has also earned the mechanism. The link between the African LSVP and the anomaly's persistent location was, for years, a paleomagnetic argument that the modelers treated with polite skepticism. It is now a shared assumption in the technical literature. The largest structure at the core mantle boundary sits almost directly beneath the region of weakest field, and the correlation is no longer treated as coincidence. That is a paleomagnetic victory, quietly absorbed. Where does the evidence, in aggregate, actually lean? This is where the treatment permits itself a small tilt, honestly earned. If you had to choose which of the two readings the current body of evidence supports more strongly, the answer is the recurring instability. Not because the reversal reading has been disproved, it has not been, but because the paleomagnetic record establishes a precedent, and the reversal reading has to argue that this particular cycle will break the precedent. That is a heavier burden than the wobble reading carries. The wobble reading has to argue that this cycle will resolve the way the previous ones did. The reversal reading has to argue that this cycle will do something the previous ones did not. Neither burden is impossible, but the wobble reading's burden is the lighter one, and in a field where the same measurements are being weighed by both sides, that difference matters. What has to be said in the same breath is that this lean is provisional. It is provisional in a way that could shift on the basis of new data over a fairly short timescale, meaning years rather than decades. If the field's rate of decline continues to accelerate, if the two lobes continue to weaken at different rates, if the reverse flux patches beneath the anomaly continue to spread, then at some point in the coming decade or two, the current event will cross a threshold that the paleomagnetic record cannot accommodate. The wobble reading only survives as long as the modern anomaly's numbers stay within the range the historical record establishes as normal. The reversal reading is waiting for those numbers to fall outside that range. Which of them happens is not a matter of debate. It is a matter of measurement. That is what makes the coming set of missions matter more than the technical framing might suggest. The Swarm constellation, launched by the European Space Agency in 2013, was designed for a 4-year primary mission. It has been operating for more than a decade past that, and the value of its extended baseline grows every year, because the longer the continuous record, the more clearly the acceleration or deceleration of the field's rate of change can be resolved from noise. The mission is now expected to operate through at least the end of the current decade, and possibly beyond, depending on the orbits of the individual satellites. Every additional year narrows the range of possible trajectories. Sitting behind Swarm is a proposed follow-on called NanoMag-Sat, developed in a partnership between the European Space Agency and the French space agency CNES. NanoMag-Sat is designed to provide the kind of continuous, high-quality magnetic measurement that Swarm has produced, but from a constellation of smaller satellites that could sustain the record for decades to come. If it flies on the current expected timeline, meaning late in the current decade or early in the next, it will extend the continuous satellite record of the field into a period long enough to make the reversal readings projections directly testable. NASA's plans for the same period are focused on a mission called the Geospace Dynamics constellation, which is designed to study the coupling between Earth's magnetic field and the upper atmosphere rather than the field's internal dynamics directly, but which will nonetheless contribute magnetic measurements at altitudes where they will constrain the models the Goddard group has been building. Alongside that, the working discussions in the geomagnetism community around a dedicated Swarm successor mission continue, and the case for such a mission has grown stronger with each cycle of the International Geomagnetic Reference Field. Here is what those missions will actually decide. If the field's rate of decline over the anomaly holds steady or slows down over the next 10 to 15 years, the wobble reading gains substantial ground. That trajectory is what the recurring instability picture predicts. If the rate of decline accelerates further, if the split into two lobes deepens rather than resolves, if the reverse flux patches at the core mantle boundary continue to spread rather than stabilize, the reversal reading gains substantial ground. Neither outcome would settle the question permanently, but either would move the balance measurably, and both are within the range of what the next generation of satellites will be able to distinguish. Which reading you find more persuasive is a question worth sitting with, because it is not a question the technical literature has decided for you. Both sides are working scientists at real institutions publishing real papers, and both have taken ground from each other over the last decade in ways that neither side started out expecting. The lean toward the recurring instability reading, as it stands today, rests on the weight of the paleomagnetic record. That weight could shift. The satellites that will shift it are already in orbit or already on the drawing boards, and the measurements they take between now and roughly 2035 will decide, more or less, which of the two readings the next generation of scientists will inherit as the working picture of what the anomaly actually is. Whatever they decide, They will decide it from data none of us have seen yet, which is, in the end, the honest place to leave a question the science itself has not yet finished asking.